Hello friends, today I am going to teach you the assembler problems of system programming. So this is the problem. We have to create the symbol table, literal table, base table and machine code, or we can say the generated machine code for the problem given. This kind of problem is called as assembly programming, and here we have to first recognize the instruction set of that programming. For example, here the test, begin, loop, data. These all are labels, or we can say the symbols. Here we are having the start, BALR, using SR. These are the machine instruction which is used for converting the high level language into the machine code. Then now we are going to see the instruction set before solving the assembler programming. So here the instruction set contain 5 types. First one is your RR instruction. In RR instruction, we are simply contain 2 bytes of data, where 2 bytes of data get divided into 3 parts. The first part is opcode, second is one R1 register, and the third one is your R2 register. Here 0 to 7 bits is used for the opcode, 8 to 11 bits used for the register 1, and 12 to 15 bits are used for the register 2. So here we are total having the 2 bytes of data in RR instruction. Second, we are having the RX instruction. RX instruction contain total 4 bytes of data, and that 4 bytes of data get divided into the 5 parts. The first one is the opcode, then register 1, then index, and then base, and last one is our displacement. So here the terms get divided into 0 to 7 bits opcode, 8 to 11 bits register 1, then 12 to 15 is the index, where 16 to 19 is the base, and 20 to 31 is the displacement. Means we are having total 4 bytes of data in RX instruction. Similarly, we are having the RS instruction. Here RS instruction contain total again 4 bytes of data, and that 4 bytes of data get divided into the again 5 parts. The opcode, register 1, here we are having the register tree, and base, and the displacement. Here again 0 to 7 bits, 8 to 11, 12 to 15, 16 to 19, 20 to 31. Again it contains the 4 bytes of data. Okay, so here we are having the register operand. Here 2 register operand are there, and base and displacement are basically used for the storage of the operand. And then we are having the fourth one. The fourth one is the SI instruction. The SI instruction again contain the 4 bytes of data, and it get divided into again the opcode part, which contains 0 to 7. Then we are having the immediate operand. This is the immediate operand. Immediate operand means the data get directly stored into the storage section, then base, and then displacement. The storage size is the 8 to 15 bits, 16 to 19, and the last one is the 20 to 31. So again it contains the 4 bytes of data. Okay, so here this is the fourth, and we are having the last one, that is your SS instruction. Now the SS instruction, it contains total 6 byte of data. It contains the 6 byte of data, and the SS instruction are rarely used in the assembler programming, but still we have to remember that there is a SS instruction. So we are learning the SS instruction. Here again it contains the opcode. The size is again 0 to 7. Then we are having the length. This is the length which contain the 8 to 15 bits. Then base 1. Base 1 contain the 16 to 19 bit. Then we are having the displacement 1, 20 to 31. Then again base 2, 32 to 35, and last one again displacement 36 to 47. So this part is used for the storage of an operand. So here we have to remember that we have to remember only the RR instruction and RX instruction. We are using RS and SI rarely in our assembly programming, but I am going to teach you how we are using and where we are using the SI and RS instruction, and here SS instruction are rarely used, so we have to remember that RR instruction always contain 2 bytes, where RX contain 4 bytes, RS 4, SI 4 and SS are 6 bytes. Now here one thing is we have to remember that for solving the displacement and base, so that we will see at the time of solving of the problem of the assembler, that how we are using the base and displacement in our programming for finding the machine codes. Now next we are going to go for the program solving, so that we will see here. As we are going to solve the problem of the assembler to create a symbol table, literal table, base table and machine code, or we can say the generated machine code. So this is the problem as we already seen the instruction set. Here first we have to find the relative address. So here the relative address or relative location can be found with the help of the instruction set. So here we are actually going to see how to use the instruction set in the assembler programming. So here you can see the test begin loop and data is there, and this is actually the labels or the symbols. This is called label or the symbols, where we are having the start using LTORC and DC. This is called as the pseudo op. So here we are having the pseudo op, and remaining SR, LA, ST all are the machine opcodes. Okay, so here first we are going to start for the relative address. So here always remember that start comes under the pseudo op, and that doesn't contain the relative address below. Then we are having the BALR. Here the test is the name of the program and start is the starting position of the program. So here we are second we are having a BALR. So as I told you, we are having the RR instruction, RX instruction, RS instruction, SI and SS instruction. So always remember, this is a technique for solving the assembly programming, that the end, if the end of that instruction contain the R, so always remember that come under the RR instruction. So we are going to add 0 here, because the here we have to start it. So here the start is a pseudo op and it doesn't contain any relative address, so here it is a dash. Then second we are having the BALR instruction. BALR contain the last, you can remember that it contain the last alphabet is the R, so it will always come under the RR instruction. This is a short technique to solve the assembly programming. Here it is a machine code, and we know that RR instruction always contain 2 bytes. So here it contain 0 because it is the starting code and it contain the 2 bytes. Second we are having the using again pseudo op, so no relative address or location is assigned to the using. Second, you can see here we are having the SR instruction, which is again the RR type of instruction, because the end of the SR contain the R, that is the register. Okay, so here what we have to do, that we have to check the previous machine instruction. The previous machine instruction is BALR, and here BALR is the RR type of instruction and it contains 2 bytes of data. So here we are going to add simply 2 to that relative address of BALR, and 0 plus 2 will become 2, and that 2 will be the relative address of the SR. Now next we are having the L. Here L is the RX type of instruction because it doesn't contain any R, so we can easily recognize that L is the RX type of instruction. We are rarely using the RS, SI and SS, so always remember that we are simply having the RR and RX type of instruction, and RX type of instruction always contain the 4 bytes. So here we are having the 4 bytes, but for allocating the relative address to the L, we have to see the previous machine instruction, and the previous machine instruction it contain the RR. RR means the plus 2. So the relative location for the L will become 4, that is 2 plus 2 will become 4. Now you can see here that L is contain the L is the RX type of instruction, and next again we are having the L, which is again the RX type of instruction. So we are going to simply add the 4 because Rx contain the 4 bytes of data. So 4 plus 4 will become 8. Then similarly A is there, again it is a Rx type, so 8 plus 4 it will become 12. Similarly ST we are having, again it is Rx because it doesn't contain R at the end. So here we are having the 12 plus 4 will become 16. Similarly we are having the A is again Rx type, it will become 20. Then we are having the BCT always again a Rx type of instruction, it will become 24. Now you can see we are having the RR instruction because it contains the R at the end. So, but we are having the previous instruction Rx type, so we are going to add 4, it will become 28 here. Then we are having the new terminology here, the LTORC. The LTORC is again a pseudo-op. LTORC, it is a pseudo-op which contain the terms which having the equal to sign. So these three are the LTORs, or we can say the literals which is present in the machine code, and we have to provide the address to this LTORC or literals which is present here. So the LTORC always contain the address of these three literals. So the first one we are having f of 10. Always remember that whatever written with the help of the equal to sign is always come under the LTORC. So here the first we are having the f of 10, second we are having the f of 49, and the third one we are having the f of 4. So we have to provide the address of these three literals which come under the LTORs. LTORC is pseudo-op which contains simply the literals, and we can recognize easily the literals which contain the equal to sign here. So here f of 10 is the f of 10, and one thing we have to remember here, then when we are having the LTORC instructions, what we are going to allot to the f of 10 literal in LTORC, that the previous one is the complete full word or not. So there is a simple technique to recognize that it is a full word or not, that we have to read the table of 4 simply. So here we are having here 2, 4, 8, 12. 4 ones are 4, 8, 12, 16, 20, 24, 28. So here we can see this is the full word having the table of 4. So here we can easily put the 32, then 36 and the 40. So we are having the full word here. You can easily recognize the literal if it contains the equal to sign, and this kind of format is there. Equal to sign is important for considering the literals for the LTORC, and we are going to allot the full word for the literals always. For that we can check that the previous relative address or memory location for the machine codes are full word or not. So here we can see that 0, 2, then we are having the 4, or we can easily recognize with the help of the 4 table. 4 ones are 4, 4 twos are 8, 12, 16, 20, 24, 28. So this is considered as a full word. So we are easily give 32, that is your plus 4 to the f of 10, 36 again plus 4 to the f of 49, and plus 4 for f of 4, that will become the 40. Then we will come to the DC. DC is again a pseudo, but here we have to provide the location to the DC because it contains the defined constant value for the program. So here we are having the 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 constant number which come under the DC. So here again previous one always we are considered the RX instruction. So it will become 44, 48, 52, then 56, 60, 64, 68. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7. Then we are having the 72, and the last one will be the 76. This many numbers get allocated only for the DC. Then at last we are having the end, that is your end of the program, and it is a pseudo. So we are not going to provide the address to the end. Okay, so this is the relative address and how the relative address get find. Then one thing we have to remember while taking the relative address of the current, we always check the previous instruction set of that particular instruction. For example, here we can see the SR is RR instruction. So for finding the relative address of the L, we have to check the RR previous instruction. If it is RR, then we have to add 2. And if we are finding the instruction for the A or the relative address for the A, we have to check the previous one. It is RX, then we have to add the 4. That's why it is 12 here. Similarly, for the LTOR, we have to remember either it is a RR instruction or RX instruction. We have to take it into the full word only. Second, we are going to find the machine code. The machine code we have to generated machine code, or we can have the machine code. Okay, so here we are going to generate the machine code for the machine programming machine instruction set only. So though there is no for the start, then we are having the second, the BLRSCR. Now as I told you, the RR instruction contain the register and register, where RX contain the register, and this is the problem we are having, that it contain here the opcode, then index, and then base. So for finding the, now here before solving the machine code, I am going to give you some tips about how to write the RR instruction contain the register and register. So here we are having the example of BLR. BLR always contain this kind of instruction. So we can write directly like this, 15,0, where 15 is the register and again 0 is under register. So we are not going to change anything in the RR instruction or BLR because it contain a RR register. Second, we are having the RX instruction. In RX instruction, the formula is simply that your register, comma, your opcode, then in bracket we have to write the index, comma, base. Now register, we can get register easily from the instruction, but we have to choose the opcode and we have to check for the index also and the base also. So that is a little bit terrible that we are going to see here. The register is easy to find, but for opcode, for solving the opcode or to finding the opcode, we are having the formula that it contain the memory location or memory address of that register, then memory address, then content, and that content we will get from the base register. So that we have to find. So we are going to check this how to find it. And so if I am going to take one example here for solving this. So if the ST 2, data of 4 is written, so here it will 2 will be become the register. This is the RX instruction. 2 will become the register, where data, for data we have to calculate the opcode, and this 4 is the index where we have to find the base. So that we will see now. Now we are going to find the machine code. So sudo doesn't contain the machine code. Here we are having the BLR. So as I told you, RR instruction always contain the register and register. So here we are having the BALR, and it contain the first register contain 50 and the second one contain 0. Again using is the sudo. So here dash. Now I am going to tell you about the base register. So always remember that using sudo contain the base register. So this 15 is our base register, and here begin plus 2, it is the content of that base register, content of that base register. So the register 15 contain the register, base register 15 contain the begin plus 2. Here we can see the begin contain the relative address. Here we can see the begin contain the relative address 0. So 0 plus 2 will become 2. So here the content of the base register is 2. Okay, so that we are not going to use in the machine code because using is the sudo. Second, we are having the SR instruction. So SR is again a RR type instruction, so 4 and 4. Then next we are having the L. So here you can see the L contain the RX type of instruction. L, then 3 is there. So here 3, then you can see here we are having the RX instruction. So we have to find the opcode here. We have to find the opcode here. So opcode get find with the help of the f of 10. Now we have to see the f of 10, the relative address of f of 10. So here we are having the relative address of f of 10, that is 32, and as I told you, the 32 is there. So 32 minus the content of base register is 2, so it will become 30. So here the 30 will be the opcode. In bracket we have to write the index. So you can see here no any constant number is given, so the index is always 0. And as I told you, the base register is always get find with the help of the using. So 15 is the base register, so here 15 is there. Then again we are having the L 2 comma data. Now data is there, 2 is the first register, data is used for solving the opcode, index and the base. So here data is present here, and here we are going to consider the data, the first value or the first relative address for the data. So here the data content 44, again we are having 44 minus 2 because the content is 2 from the base register, it will become 42. So 42 is there. Now you can see the data contain the constant number 4, so that 4 will become the index value, and base register is here 15 from the using. Then second we are having the A is content 2 comma, then f of 49. F of 49, the relative address is 36, so 36 minus 2 will become 34. 34, again no index or no constant value is present, so 0 comma 15. Similarly for ST we are having again data, so ST 2 comma, the data will become 42, as we are going to directly take from the previous data, 42 4 comma 15. Okay, then next we are having the A 4 comma f of 4 content 40, 40 minus 2 it will become 38, so 38 0 comma 15 because no constant is present there. Now you can see here we are having the BCD, that is something new machine instruction we are having, but we are going to solve it as usual with the help of the RX instruction. So the first register is 3, and second we are going to find here nothing is given, so we are going to take the 24 here. So 24 minus 16 will become 24 minus 16. We are going to find for the BCT, as BCT is a new term for us, it is again come under the RX instruction, so we are going to find it similarly as we have find for the previous machine instruction. So 3 is the first register, then you can see here no constant or no symbols is given here, no literals is there, directly it contains the immediate value. So here the location of that particular is 24, so 24 minus 16 will become 8, and the content of our base is 2, so it will become 6. So here we are having the 6 value 0 comma 15 because no constant is given. The next one we are having the BR. So always remember the BR is the branching, and that branching is always get converted into the conditional branching, so it will become BCR always, and it will become 15 comma 14 because this is the RR instruction, and RR instruction always have 2 registers, that's why the BR get converted into BCR 15 comma 14. Then we are having the LTORC. So LTORC is there, we are simply going to write the constant value for that, and then the constant number for that particular allocation. Okay, so until your 0 you have to write. It should come in the single line because of the blank page, or it get mismatch. So we will see the next table. So this is the assembler programming, the basic instruction, the relative address and the machine code, and now with the help of this we are going to generate the tables. Okay, so that we will going to see. Now this is our program. As now after generating the machine code, now we are going to create the table. So the first one is the base table. So for the base table we require the register number and the content of that register. So as I told you, the using always contain the base register and the content. Here begin, the value of begin, from here it's 0, so 0 plus 2 will become 2. So here the register is 15 and the content of that register is 2. So here you can see there is no other using is there. So we are having only the one using, so the only one register and their content is there. Now the second table, this is the base table, the second table is the symbol table. Now the symbol table simply contain the symbols, the value and the relocation, means the value get relocated or not, that we are going to see here. So as I told you, the test begin, loop and data, these are the loops or the labels or the symbols we are having. So the first one is the test, then we are having the begin, so we are going to write it simply, and then we are having the data. So the test is the starting, it doesn't contain any value, so 0. Begin is also the starting, it doesn't contain any value, so 0. Then we are having the loop, and when we will see, it contain the value a, and the last one we are having the data contain the value 44, that is the relative address of that particular symbols. Now reallocation contain the two parts. The reallocation contain two parts. The first one is the allocation absolute and the second one is the reallocation. Means if the value doesn't get changed throughout your programming, then we are going to provide the absolute, and if the value get changed in the programming, then we are going to provide it the reallocation. So here all are reallocation because somewhere it is used in the programming. So this is your symbol table. Now the last one is your literal table. So literal tables, always remember, the literal tables contain all LTORCS values. So here the first one is the literal, then we are having the value of that literals and again the relocation of that literals. So here, as in the program, we are having the three literals, that is your f of 10, f of 49, f of 4, and we are going to recognize the literals with the help of the equal to sign. So here we are going to use it. The literals are f of 10, then we are having f of 49, and the next one is your f of 4. So three literals are there. So the location of literals we will get from the LTOR, that is your 32, 36 and 40, and again the reallocation is there or the absolute is there. So we are going to reallocate it because we can somewhere using this in the programming. So this is the end of the assembler programming. Here we have done the base table, symbol table, literal table. We have generated the relative address of the program, and we have also generated the machine codes for the program of the assembler. So thank you so much for watching our video. It was nice to see you again in our next video. Thank you.